Welcome to another Foundry tutorial on Cara VR. I'm Daniele Bernabei, lead developer of Cara, and I'm here to talk to you about generating stereo content using Cara VR. Cara is a powerful tool for monoscopic stitching, but it is also great for generating stereo content, and it can offer you a large degree of control on the final look of your projects. So let's get started. Now, generating stereo for VR shares all of the same problems, issues that you have when generating stereo for traditional flat content generation, which means that you need to regulate the amount of parallax that you have between the left and the right eye. The parallax must be such that it allows you to perceive the scene as three-dimensional. And if it is too much, then it can break the illusion. The brain cannot reconcile the left and right eye differences. If it is too little, then the scene will appear flat. Also, when dealing with stereo, you decide where to put content in relation to your screen plane. Content can have positive or negative parallax, which means that in the case of negative parallax, the objects will appear as sticking out from the screen, and if it is positive parallax, they will appear to recede into the distance from the screen. Now, all of this, if you are familiar with how stereoscopic content is generated traditionally, can be achieved by either regulating your cameras when shooting or by tweaking the scene in post. So the distance between the cameras in a standard stereo setup is what is called the interaxial distance, and that is what changes the amount of perceived three-dimensionality in the scene globally. And the other control between the two cameras is instead the convergence, which can be achieved either by towing in the cameras by pointing towards the same a closer point than infinity, like this way, or better yet, as I'm doing right here, you can slide the position of the film back in the cameras, and that will alter the geometry of your projection in the same way. Now, when you alter your convergence, then the two frusta of the two cameras, instead of being perfectly parallel and converging at infinity, they converge on a plane that is closer than infinity, like, for example, in this situation here. If I see the scene from exactly above, here at the intersection of the two viewing frusta of the two cameras, then I define my plane. Everything that falls behind this plane will appear as receding into the distance, and everything that's in front of it will appear as coming towards the viewer. Now, there is a lot of consideration to be had about stereography that go beyond the scope of this tutorial. So if you are coming to stereo VR from monoscopic VR but have no previous experience on stereo, I will definitely recommend you to delve deeper into the finer issues of stereoscopy. But for the purpose of this presentation, this will give us the basic concepts on which we're going to work in Cara. And let's move on to the three ways that you can generate stereo content using Cara, depending on the setup of your rig and how you're going to use Cara itself. Now, usually when you're generating stereo, instead of having a monoscopic rig arranged in a spherical way like this one, you have a rig of stereo pairs arranged probably something like this, where camera 1 is paired with camera 8 in this case, 20 with 9, and so forth. So if you stitch together all of the left eye cameras and separately the right eye cameras, provided that there's no misalignments between them, then you can get out of it a stereoscopic stitch. So let's see what this actually means in practice. Now, I have here a simple geometric scene these gardens, this from Kew Gardens, this archway. And I've rendered out from all the camera positions in my stereo rig using the scanline renderer. So I've got these pairs, these stereo pairs arranged like this, left and right, and then left and right, and so forth. So bringing in my renders, this is all my left eye cameras. I have set up a camera solver with the same positions as the cameras. And if we take a look at the result of this, then you can see that we have a panorama of my archway from those cameras. Now, if I just copy this camera solver and use it exactly as it is for the right eye cameras, it will provide me with the equivalent right eye panorama. And let's take a look at it. And there it is. This is the left and this is the right. So there are some misalignments here that will be solved by just putting in a C-stitcher. So the only thing that I need to care about is that it's set up in the same way. And if we take a look at the result of this, and compare it to this one, then we have a left eye, right eye panorama. Now, the problem with this approach is that, as I said at the beginning, it requires the camera to be perfectly aligned. It requires to be no vertical or diagonal shifts between the camera pairs. And this is something that will probably not happen in real life unless your rig setup is extremely precise. And the second disadvantage with this is that if you change the convergence settings in the camera solver and the stitcher, this will actually not affect the stereoscopic convergence. So you might recall about convergence from the introductory tutorial. And in the context of stereo, convergence acquires a different meaning. So the same convergence settings that can aid us in finding the right distance at which we want objects to snap together, in the context of stereo, it represents the actual screen distance. So same way as with standard stereoscopic cinema, objects that are going to be beyond that distance will exhibit positive parallax, and objects that are closer than this distance will have negative parallax. Now, if we change convergence settings on these two stitchers, and say, for example, we converge at 2, it will actually affect the quality of our final stitch in the same way that changing convergence changes the monoscopic content. You can see that everything has been shrunk down in the sense. This is a very strong value for convergence for this scene, completely unnecessary. But I'm using it here just to prove a point that actually, if you take a look at the two different stitchers, then there is no much, it hasn't actually affected the stereo convergence. So everything looks as if it is far away from the camera. So the second way of producing stereo using Cara VR is by inputting all of your left and right eye pictures to the camera solver. So you would select everything in the right order in this case. Let's check that the order is correct. Yes. Then match. And solve. And you can see that the end result is quite confusing at first because cameras are overlapping together. And you can see these ghosting effects are not due to an improper alignment, but are actually due to the parallax between the left and right eye views. But what you have gained by going through this method is that if you look at the three-dimensional layout of the cameras, you can see that the camera solver has found some vertical inconsistencies between the different cameras. So as expected, it has found that these cameras are actually pointing in opposite directions, this one and this one. You can see they're flipped, and actually they're flipped here as well. You can see the reels here are here, and they actually found also the diagonal inconsistencies. So okay, when you look at this picture, it's how do you get some stereo out of this? So a camera solver by itself cannot produce stereo, so you need to add a stitcher in order to do so. But before you add the stitcher in the camera solver, you need to make sure that all of the left eye cameras for this particular setup are set up to input view left, and all the right ones, which are 5 to 8 in this case, are actually set to be the right view. So this way, when you pass it down to the stitcher knows which ones to use for left and which one to use for right when you do enable stereo stitch. So let's take a look at the result of this, and let's do a split and join on the stereo so that you can see better the two differences. So this is a left view and this is a right view. Left and right, left and right. So these cameras are producing the left view, and these cameras are producing the right view. And the stitcher, having received as input through metadata from the camera solver the positions, it has reconciled most of the vertical misalignment problems. There are still some issues going on here that need to be addressed later on, and you can see in another one of the tutorials how these are fixed. But as a starting point, this already corrects a lot of problems that you have with this kind of setups. But there is an additional bonus, which is the use of convergence is actually impacting stereo in the way we would expect. So if we take a look, if you examine closely right now where this scene is converging, then roughly it is converging around this part here of the scene. So you have to take into account that even if the camera solver the value of the convergence here, it can be meters, it can be whatever you want it to be, it's units, right? The only thing that determines actually what it's going to do is this is a value that is relative to the rig size. So to achieve the same result, you can either increase the rig size or decrease the convergence value to bring it closer. So let's try and have a different value for convergence and see the difference with this. So let me add actually a different camera solver and another two left and eye. A C stitcher. And let's have in this C stitcher here, it's another stereo stitcher, but that converges at 3, let's say. Okay, let's take a look. So you can see immediately that the global appearance of the scene has changed. But beyond that, the convergence point has moved forward. It has moved around here. So this is the plane where this is actually converging. And there are artifacts that have been introduced here because of the nature of this particular setup. But this is to understand the effect that convergence has not only on the way the scene is solved in camera solver, but in the way it is finally stitched. So another way to analyze how our convergence has changed is through the anaglyph. Let's give a little bit of color to both of them. No, connected to here. So you can see how now the parallax in the second example on the guy has diminished, and how it is actually converging on the coat behind him, and how from this setup to this setup the parallax on the face of this man at the back of the bar has strongly increased. So compare these instead to this setup here, in which, okay, we had two C-stitcher set up with convergence 2 and 2 in this case. And let's have another two C-stitchers that are the same default convergence settings of 10. So let's use the two C-stitchers that converge at 2, left and right. And let's join this one with that one. Okay, and pop in the anaglyph. Zero two. Take a look. Okay, you can see that actually at the far on the far wall, it looks like the parallax has remained the same. Roughly, it hasn't changed that much. It's the change in convergence between the two stitcher is dramatic, and in fact, the global appearance of the scene changes, and this one is really hard to reconcile in its in the stitching process. But the parallax has remained the same. Again, take a look at this one and you'll see that instead the changes have been quite dramatic. Okay, so with this method we've seen that there's two advantages. We got we can fix the different orientations, the misalignments in your rig, and we can use the convergence to regulate where the screen plane of our scene is. Now, there is yet a third way of performing stereo, and it is actually the most advanced that you can have with Cara. But that kind of setup, it's only possible when you have rigs with a large amount of cameras, or with fewer cameras but a large amount of overlap between them, because you have used possibly very wide fisheye lenses. So we have the setup here, captured with the Odyssey rig, and I'm gonna bring in a camera solver, and just, I don't care about metadata, I can just match and solve. This scene is pretty easy to match and solve. There you go. And as you can see, every single camera has been used to produce this the final composite lat long. And in order to use the Omni Stereo, you need to make sure that these stay at the default setting of all. Camera Solver by itself, again, has no concept of stereo production. So in order to use this, you have to pop in the C stitcher. And again, you gotta enable stereo stitch. So you might have noticed even before that when you enable stereo stitch on the C stitcher, a lot of new views get created. So if you got only 8 cameras, then the C stitcher will generate for each one of them the left and right equivalent. And the difference, what is happening here is that these left and right cameras show you how each of the individual cameras have been used to produce the left eye and right eye. Because the difference with the previous approach of producing stereo is that every single input in this case is now used to produce both the left and the right. So the C stitcher is performing a slit scan rendering, a form of slit scan rendering. So let's take a look at how it works exactly. Now imagine we have a rig that is laid out like this. So this is an approximation of a rig with a large number of cameras, or with smaller cameras but with a large overlap. This is only 6 cameras, so that the graph doesn't become very difficult to read. But imagine that they had more cameras than what you're seeing right now. So what I want to do when I do slit scan rendering is try to construct 2 panoramas as seen from virtual camera's position, located like this. So these are my left and right eye cameras, and in a similar way as I do with monoscopic stitching, in which I try to reconstruct a virtual panorama as seen from a camera located at the centered position, using the cameras that are laid out on the ring. In slit scan rendering, we want to do this for the left and right eye camera separately, and for every column of pixel in my image, I want to render from a different position of these cameras. So what I mean by this is that if I want to render from, this is the starting position like this, will be rendering the first column of pixels, and then as I want to continue constructing my panorama, I will rotate my virtual cameras around their common axis like this. And as they rotate, they generate a slit that it's then accumulated in constructing the final panorama. So a slit for the left and a slit for the right eye. So as these cameras rotate, you can see the frustum here, that is sort of a visual representation of the slit that they're gonna try and construct. Now, as the cameras rotate, they intersect several different cameras. Like for example, in this case, my 2 virtual camera, they look through camera 14 and camera 7. So the slit that is gonna be rendered in a final image is gonna be constructed with both camera 14 and camera 7. Warping it to be seen, so the image from camera 14 will be warped as if it was seen from this position and that position in constructing the left and right panorama. So that's why for each of your individual original cameras, then after the stitcher you get the left and right version of that same camera, and they have a very different mask and appearance. Now, there is a difficulty when dealing with stereo panoramas, which is the ambiguity that you have at the poles. And what I mean by that is that imagine that you have a viewer sitting like this in your default position. So this is the front. If you are wearing a headset, maybe your monitor is like this. And then the viewer decides to look up and all is fine. And you will imagine that the left and right picture have been constructed in the same way at the pole up here, in the same way as when looking forward. However, imagine now that the viewer has rotated, is looking at the back of the chair, and again looks up, And we have a problem here, because now the viewer expects the left and right eye to be exactly inverted from what they were before. So from here to there, this is simply not possible. So how do we decide which priority to give to the frontal position? Well, that would be a bad idea, because otherwise looking up from behind will definitely cause some very disturbing inconsistencies. So what is the solution to this? Is avoiding to have stereo at the poles. So this is what we have with the fall-off controls. And what is meant by that is that as we pan around the same normally as we've done before, but as we tilt up, then we reduce the interaction distance until it is 0, so that there is actually no stereo at the poles. There is no parallax either up or down. So it's true that this introduces some strange effects, especially if your rig is close to some nearby objects on the floor. This object will be pushed back at screen distance. It usually is not that much of a problem when you've got just sky above, but it is something to be definitely aware of in the process of slit scan rendering with the C-Stitcher. So let's go back to the C-Stitcher and see in practice how this thing affects the look of your lat long. So we got here a left and right eye panorama merged together with the anaglyph. And let's take a look at this part of the scene here. It's easier to visualize. So first of all, let's control the eye separation, so the distance between the two virtual cameras. If we reduce this, then we will expect the parallax to be reduced globally in your entire scene. So if we put it to 0.3, you can see now that this has gone, this has changed significantly from 0.65 to 0.3. They're now sort of reconverging together. And what I have here is linear fall-off type. So fall-off type is these three knobs here. The fall-off type, the start angle, and the separation fall-off control the shape of the function that brings back the interactional distance between your cameras back together to 0 when looking at the pole. So linear is a much stronger way of going from a normal parallax to 0 parallax at the pole. We have something more soft, which is the cosine. So if we switch to cosine, you'll see that there is there is more parallax now at this corner of the table that is comparable to what we have here on the glasses. If I go back to linear, you'll see that then it starts reconverging back to 0 parallax as the gaze goes down. So again, linear, cosine. And this should give you all the controls that you need to actually match your stitch panorama with whatever you render, for example, with an external application if you're doing CG integration, or with a C-ray render, which has exactly the same parameters for controlling stereo appearance as you have here in the Stitcher. So to recap, we've seen the 3 ways that you can generate stereo in Cara. We've seen the bare bones approach of just producing 2 stereo panoramas independently without having them matched together. We've seen a more comprehensive approach of having all your input cameras left and right in the camera solver, and that gives you the ability to actually reconcile some misalignments and to use the convergence to control the convergence in your stereo. And finally, we've seen the omni-stereo approach that allows you not only to control the convergence, but also to control the eye separation and the fall off at the poles. So I hope you've enjoyed this tutorial. And this was Daniele Bernabei from Foundry with another Cara VR tutorial.